put together a sign diagram here. So we skipped that, and some of you were like, yes! And others of you are like, no, I like the sign diagram, so trying to please everyone, but.
So how do you know whether it's a relative min or a relative max?
It depends on the concavity. If it is negative in the second derivative, it means that it is concave down, and then look what concave down looks like. You have a relative max. It's concave up, you have a relative min.
So is it just chance, or is it going to happen every time where like your critical numbers can also be used to get, I'm sorry, I don't know how to explain that. So you use 2 because it's less than 3 to plug into the second derivative to get what the minimum is. And that just happens to be the same maximum number for the critical number. See what I'm saying?
Like the number that I happen to be picking happens to be in the interval?
Yes.
No, it's not chance.
Because I'm thinking like, what if,
What if you get a critical number that is your point of inflection?
right.
Then, remember, if it's a point of inflection, it doesn't have a max or a min.
Okay, okay.
And it happens. Remember, we
Yeah.
saw that with the previous example.
When I put in the critical numbers into the second derivative,
Uh-huh.
it's -6 and 6, so that determines whether it's.
Because it's negative, the -6 is telling it's concave down, the positive 6 is concave up. Question?
No.
Any other questions? Yes, ma'am?
And are we only doing that with the critical numbers to find the concavity? Or no, are we using?
The reason we're using the critical numbers with regard to the concavity is because it tells us whether they're a max or a min. So it's like 2 birds, 1 stone.
So then when we graph it, we're still gonna be using like the ordered pairs from the first?
Correct.
Okay.
Correct. So now, if we were actually gonna graph it, we're back to here, right? And if f of 4, what is that? I don't know, plug it in here and tell me. 4 cubed minus, how much is it?
Oh, so the actual points?
Actual points.
So that'd be 27 minus 81 plus 72, which goes, or, I'm sorry, 64 minus 144 plus 96, which goes to 16.
So, on my graph, 1, 2, 3, 4,
Yeah.
and 16. Oh, but I think this is not, I don't know where this is supposed to be. Let me not do that yet. 4 and 16, what about f of 2?
That's 20.
Okay. And what about f of 3? So, 16, 18, 20, 1, 2, so 2 here, 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 and then, oh, it's terrible. This is kind of what we see. Oh. But, relative max, relative min, point of inflection, this is where it starts to change at 3. The concavity. Yes? No? He's saying yes, he wasn't here, so yes. Can I erase it?
No.
Okay.
Sorry.
You're fine, you're fine. We'll freeze it real quick. Okay, for those of you that aren't still writing, consider the following function. F of x equals x cubed plus 3x squared minus 9x plus 7. And the directions say to sketch based on critical numbers and concavity. So start that if you're not still copying other stuff.
It's a new problem.
New problem, x cubed plus 3x squared minus 9x plus 7. So I was trying to give you a little bit of lead time to let you work, see what you come up with. I'm gonna close that for a moment. X cubed plus 3x squared minus 9x plus 7. When I worked out the first derivative and set it equal to 0, my critical number is -3 and 1. How many people got that? Fantastic. Any questions about the critical numbers? Then I take the second derivative and set it equal to 0. Because it is a second, I can differentiate it again. And when I set that equal to 0, I get -1. Now, to the left of -1, I have -3. And to the right of -1, I have 1. And when I plug those in here, I get -18 plus 6 or -12. So that's big negative, which means it is concave down. And then at 1, I get 6 plus 6 or +12. Positive, which means it is concave up. So at my critical number, -3, what do I have? Relative max. -3. And at this other one, 1, I have what? A relative min. And what is -1? What do we call that? IP, inflection point or point of inflection.
I'll be the midpoint between the two.
Not always, just so happens to be in this case. It's not always. So what do I need to graph?
Your
Or you can
pair.
start with 0, -9, and then start,
So he likes the point 0, -9. How come? Because
because
it's
it's an
easy.
easy one. And then you go ahead and plug in the critical numbers, and then the inflection point.
So
Connect the dots.
-3, 1, -1, and where do they all get plugged into?
The original.
The original equation, so
Oh, -3 is 34,
-3 goes with 34,
and 2 for 20.
1 is 2.
Uh-huh.
That's 0.
No, that's what we-
Oh, yeah, that's 3 plus 6.
Negative
What's -1?
8.
Oh, because I'm not plugging it in there. Okay.
We look at the right equation.
So we get these 4 points, and these are actual points. Their behavior is determined by the first and second derivative, but the points themselves come from the original equation. Everybody good with that? Yeah.
So why'd you start with 0, -9?
Because it's an easy one.
Because Micah told me the reason is, when we plug in 0 for the x's, 0, 0, 0, and it shouldn't be -9, it should be 0, 7.
Lo siento. I was just looking at the big thing that was caught my attention.
Right here,
The y-intercept is.
y-intercept.
Got it.
Y-intercept. And it's just another point to make your graph more accurate. Do you have to? No. This is the y-intercept, and it's optional. But it just helps, you know, make your graph better, more precise. So we've got -3, 10, 20, 30, 4. Gosh, it's like here. 0, 7 is like here. 1, 2 is there. -1, 18 here. It makes it harder for me, because now you're making me go through that point, and I have to think, where's the concavity? It's okay. So we're coming up to here, like this. And then I'm going down to here, but at that point, I'm gonna change directions. Roughly like that.
Inflection point would be -1.
My inflection point is this point, this one. The -118 is the inflection point. The other two are the critical numbers. And that's this one and this one. And Micah just made us graph the y-intercept because he liked it.
Yeah.
So, that's equal. Here's our information in a nutshell. Use the derivatives to sketch. The critical numbers are -3 and 1. The inflection point is -1. When we plug those in, we get the -3, 34, 1, 2, and -118, 0, 7, because you can. And then you look at the graph to the far right, you can see the points, which, you know, it looks very much like our graph. Much better. Okay. That is the conclusion of section 3.2. Today we need to look at section 3.3. That was 3.2. 3.2. I know, right? Now, section 3.3, we're gonna talk about optimization, which this is the practical application of all of the math we have been practicing. So it's nice, because it's things that it's like, oh, this is why we have to do it, not just, here, work these problems. Now, that being said, they are the word problems. But it's nice because it relates to what we've been doing. So, many of these consist of optimizing a function, that is, finding its maximum or minimum value. Well, max and mins, where does that come from? The first derivative, so there we go. One of the principal uses of calculus is that it provides a very general technique for optimizing functions. We'll concentrate on applications of optimization. We will optimize continuous functions that are defined on closed intervals, or functions that have only one critical number in their domain. Because otherwise, we have so many things to look at and lots of moving parts. Most applications fall into these two categories. The wide range of examples in this section will demonstrate the power of these techniques. Absolute extreme values. An absolute maximum is the largest value of the function in the domain. So up to this point, we talk about relative extreme, where it's relative to the points around it, but an absolute max is the highest possible value. Similarly, an absolute min is the smallest value on the domain. Absolute extreme value is a value that is either max or the min, and they correspond to the highest and lowest points on the graph. So, if on this picture, if we were to restrict the domain, we could say, yeah, we have an absolute max and an absolute min. But since it's not restricted and we have these arrows going in both directions, these are both, this is a relative max because this arrow is going to go up higher than it. This is a relative min because this arrow is going to go lower. So that's the difference between relative max and min and absolute max and min. It just depends on if there's some outlier that will go higher or lower. So for a given function,